Alright, so today we're going to be looking at projectile motion part 2. So the series is a 3-part series that looks at the 3 trajectory cases in projectile motion and tries to get you used to the 3 different trajectory cases so that you're able to solve questions that involve these cases. The first part will be linked in the comments below, and it basically talked about the first case when an object is launched off of a level ground at an angle and lands back at a further point down the same level ground, right? So that was the first case. And if you haven't seen the original video, the video part 1 does have some general rules for projectile motion, so you can take a look at those as well as an overview. It will be linked in the comments below. So let's get started with case 2. So case 2 is when an object is horizontally launched off of a platform. What does that mean? That means that, for example, if you're standing on a cliff and you throw a ball, but not upwards, you throw it literally at a horizontal in a horizontal motion, and that ball falls off the cliff, which then creates this type of curve, right? A better example is, for example, if a ball is rolling off a table, right? If a ball is rolling off a table, it rolls off and creates this type of motion. Just some quick general overview of this case. Initially for VI, there will be a VIX because it is a horizontal launch. VIX has a value. However, because it's a horizontal launch, there's no y component. So VIY, right? VIY, the initial velocity in the y direction will be equal to 0, right? Because it's a horizontally launching object, right? There's no initial y component. However, there will be a VFY, right? So this will have a value, right? Let's just say x for now. But this will have a value. So essentially, you'll have to calculate the questions may ask you to calculate the VF, right? Given VF, given the VI, right? And then you'll have to use the two components to calculate it. But again, we will look into that in a bit. And then just a quick other few components. So there is an initial height, so the height of a cliff, for example. And then there's a range, or in other words, the delta dx. So the height is otherwise known as delta dy. The range is otherwise known as delta dx, right? So let's get into the case-based rules. What does this mean? This means that for questions that have this type of setup, these rules will apply. So you can use these rules as a general kind of overview for these questions to solve them, right? So the first thing is essentially we're going to be using a formula. Vertical position equals 1/2 gravity times squared plus h. What does that mean? That means that your position, so your vertical position, so your delta dy, right, is equivalent to your 1/2, right, your 1/2 acceleration times squared, right, plus your height, right? And now in this case, delta dy doesn't necessarily mean what we labeled it here, right? Delta dy just means any position, right? Any position in the curve. So it could be here, could be here, could be here. It just means any position in the curve, right? It's your vertical position. Depending on your time, obviously. So basically, right, what we're going to be doing here is we're going to be rearranging this equation, right? And we're going to get how to solve for h, for example, right? So we have the equation -1/2 gravity times squared plus h, right? So let's assume our vertical position is 0, is because we're starting at this cliff, right? We're starting at the top here, right? So obviously our vertical position is 0, right? And we're trying to find this h, so whatever this value is, right? How tall the cliff is, essentially. So we plug in 0 for vertical position, right? And then we rearrange this equation. So we move this h to the other side, right? And the way we do that is we cancel out h here, right? And that subtracts h here, right? Better way to write this would actually be like this. So this would be 0 minus h, right? So these cancel out, and then on this side you'll be left with negative h equals -1/2 g times g delta d squared. And as you know, the negatives will cancel out, right? That's why there's no negative in your final step, and you're left with this formula right here for your h, right? And this is important because rearranging this formula can get you your time, right? And we'll look at that in the next step. So a little bit of a more in-depth version, right, of this rearrangement, or how we derive this formula, is seen here, right? So your delta dy, so this is a kinematic equation. Your delta dy is equivalent to your vi times your delta t plus 1/2 acceleration times squared, right? And now you know that your vi is equal to 0, right? So your viy in your initial position is equal to 0. Why are you using viy? Because you're solving for delta dy, right? So you're looking for only the vertical components, not the horizontal, right? So when you plug in your viy to be 0, this term cancels out, right? So now you're just left with this term, right? And as you can see, it's the exact same formula that we've derived here, right? So this is just another way of deriving it using the actual big fat kinematic equations, right? And now using this formula, we can now derive a formula for delta t that can be used to find the time at any position within the curve, right? So this can be interchanged between one another. The next general we're going to look at is for your range, right? Your delta dx, so the total distance traversed in the x-axis, right? And now we know from basic kinematics that because vx is constant, or vix is constant, right? This is the formula that we'll use. So when v is constant, this is the formula you will use, right? So if you notice, it's the exact same formula that we've used here, right? The only difference is we replace v with v of x, right? So vx. So whenever you want to find the delta dx, or if you want to find the vix and you have the delta dx, you can use this formula and rearrange it, right? So if you want to rearrange it for vix, it would look something like this. Delta dx over delta t equals vix, right? And you can also do it for time, right? So if you were to do it for time, it would just be delta t equals delta dx over vix, right? So let's continue on. The next general kind of rule you need to know here, or formula, is your theta, right? And this is important because when you calculate your final velocity, right, you're going to need to get the angle, right? You're going to need to get the angle. So to get that angle, this is important. This formula right here is important, where vi is your vfy component, and your vx is your vfx component, right? And remember, your vfx is just equal to your vix, right? Because they're constant along the entire path that is being traversed. And this was in the general rules from part 1. So the next thing is a formula similar to Pythagorean theorem, which actually is Pythagorean theorem, just completely rearranged for v of f, right? So this formula gives you vf using your two components, vfx and vfy, right? So once you have those two components, you have to solve for vf, and then you have to solve for the angle vf, and then you'll be able to get your final answer, right? So the next part, or the next rule is just this is more so of a kind of assumption that you're under constant acceleration. So in most projectile motion questions, at least in the beginning, you will be given constant acceleration, meaning that your velocity increases by a constant acceleration curve. Acceleration will most likely just be negative 9.81 meters per second throughout the path of travel. So in this case, right, you can say that your VFY is actually equivalent to your negative acceleration times your delta t. Now, why negative acceleration? Because this negative acceleration is actually negative 9.81, right? The negative is a direction, right? Because the path that the gravity or the acceleration is pulling you is downwards, right? So that's why it's negative. 9.81 is actual magnitude, right? And so if we continue this, right, and then we use a kinematic equation, VFY equals VIY plus acceleration delta t, right? Again, we can sub in VIY equal to 0, right? So this would actually be 0, right? So VIY would be equal to 0, right? Minus acceleration delta t, right? And this would give us our VFY equals negative acceleration delta t, right? And now here's a quick question for you. So if that acceleration is negative, right, why is this acceleration here, right? So why is this acceleration here not negative, right? Why is acceleration not here not negative? Why did we not put a negative 1/2 at squared, right? So the thing is, we haven't shown it in this example here, but when we actually plug in our values, right? When we actually plug in our values, let's say we're just using arbitrary time like 2 seconds. So when we actually plug in our values, we're actually going to plug in a negative 9.81 there, right? And then that's how you're going to do it. So you have to make sure to always remember to plug in negative 9.81, not just 9.81 even. So moving on, let's try an example, right? So in this case, we have an example where a ball is rolled off of a cliff, right, that is 45 meters high with initial horizontal velocity of 12 meters per second. So we have to calculate the time of flight, all right? So we have to calculate time of flight, and then we have to calculate the final velocity. So the way I like to approach these questions, or any type of physics question, is first things first to draw myself a diagram, right? Doesn't have to be anything crazy, just a simple basic diagram of what's kind of happening in the question, right? So I've drawn that diagram here, right? So I've drawn that diagram here. Of the ball rolling off the table, right? And I've labeled my components here. So VIX is 12 meters per second, right? Because it's velocity in the horizontal. My VIY is just 0, right? I know that because it's horizontally launched. And then my H is just 45 meters, right? So another general approach I like to take when solving physics questions is writing my givens and unknowns, right? So I wrote my givens here, right? So my givens are here. So I have my VIX, my VIY, and my H, right? So I recommend using this format for every physics question that you do, at least in the beginning, just so you can get used to visualizing the question, visualizing the solution, and tracking what you're doing, right? So you don't make as many mistakes along your solution. Your unknowns I've written as my delta T and VF, right? Because that's what we don't have. So let's start with the actual calculations, right? And again, remember, we've come up with these equations beforehand. So we can use these equations to now calculate what we need, right? So first of all, we need to calculate our time of flight, right? So we have our delta t, right? We have our delta t equation, which was derived up above here, right? So we have our delta t equation. Now what do we need to do, right? We need to plug everything in, right? So if we were to plug everything in, 2 times 45 divided by 9.81, right? So it gives us 3.03 seconds, right? You might be asking why I didn't plug in the negative to acceleration here, right? Because up here, when I derived for this equation, I actually already factored, right? I already factored for the fact that the negative was there, right? If you notice here, right? If you notice in this equation also derives this, right? And in this equation, I showed you how the negatives cancel out, right? So I've already taken into account the fact that acceleration is negative. Therefore, when I go to this equation, I don't need to factor in the negative again because it's already been done beforehand. So I found my time. Right, so that's one thing done, checklist. The next thing is, let's calculate our VF, right? So to do this, again, we have our VFX, but we don't have our VFY, right? So we don't have our VFY. You might be asking, why do we have a VFX? We'll see that in a minute. Or you can actually see that right now, but I'll explain that in a minute, right? So your VFY is calculated by this equation that we've derived up above, right? So it's pretty simple. Negative 9.81, the acceleration, times your time, which we found in the step above, right? So it's pretty simple to get your VFY. It's a very straightforward solution. Now for your VF, right? What do we say when we're calculating our VF? We need to use the Pythagorean theorem that we devised, right? The square root of VFX squared plus VFY squared, right? First, let's get our VFX, right? And what do we say our VFX is, right? So as a general rule, VIX is always equal to your VFX because VIX is always constant. And this goes for any projectile motion question, right? VIX is always constant. It's because acceleration is not, right? Acceleration is not seen in the horizontal. Right? It's only in the vertical, which is why VIX is constant, right? And this could be seen for any case. Again, these are some general rules that I talked about in my part 1, which will be linked in the comments below, so you can take a look at that as well. So let's move forward. Using our VFX now and our VFY that we calculated in the last step, we managed to solve our VF, right? And you might be asking why I didn't plug in a negative here, right? That's mainly because even if I did plug in a negative, right, 29.7 squared, right, it would still give me the same answer as 29.7 squared. Right, so these two answers would still be equal, right? So whatever x is here, x would be here, right? So it would be the same answer irrespective, right? And also because negative is the direction, right? 29.7 is a magnitude, right? So that's a magnitude of my velocity. That's what I'm going to be looking for. Now the last part is to calculate my angle for VF, right? So the angle is a simple equation, theta equals tan of -1 or tan inverse VFY over VFX, right? So this is the solution for the angle. So my final VF, right? So my final VF is equal to 32.05 meters per second, right, with an angle, right, with an angle of 68 degrees, right, with an angle of 68 degrees. That is my final VF, right? You might be asking, how did I get this tan equation? That is based off the SOHCAHTOA, which again I talked about in my part 1 video, so you can rewatch that to understand more about that one. Now we'll be releasing a trigonometry video soon, so you can also watch that if you do have trouble with that. If you do have trouble specifically with trigonometry, you can reach out. If there's any specific questions you want me to do, I can do those as well. So that's essentially part 2 of projectile motion. So that's case 2. We will be going over case 3 in the next video. So to follow for more, and if you guys have any specific questions, then you can reach out. And if you have any questions about this video, you can reach out and message me. You can ask in the comments, and I'll be happy to answer.